Okay, we are going to be introduced to E. Now, if you recall, compound interest means that your interest rate is going to be applied to your investment or to your loan as many times as it's compounded per year, but you also have to divide the interest rate by as many times as it is compounded. So we've had the formula already where our total is equal to our principal amount times 1 plus r divided by n. Here's the part where you have to divide it by the number of times it was compounded, and that's raised to the nt. So let's say you have $1 and you get an interest rate of 30% a year. Remember, when you are using this interest rate, you have to use it as a decimal form, so we would use 0.30. Well, if your interest is just compounded once a year, then you would have 1 times the quantity, 1 plus 0.3, because 0.3 divided by 1 is 0.3, raised to the 1 times 1, which is just 1. So you'd end up with $1.30. But if your interest is compounded twice a year, then you would have to use half the interest rate here. So we have to take our 0.3 divided by 2 here. So we take our initial investment, our principal, times the quantity 1 plus 0.3 divided by 2, and this time it's raised to the 2. Again, it's times 1 because we're just looking at it for 1 year. You'd have $1.32. If your interest is compounded quarterly, well, instead of dividing by 2, I would have 4s in there then instead of the 2s. If it's compounded monthly, they would be 12s. If I left it in there for 7 years, then I would have a 7 up here in for my t value. Well, now, what if you wanted to compound it every minute, every second, every millisecond of every day during the year? In 1683, the mathematician Jacob Bernoulli considered the value of this, our growth rate, basically. If you think about our formula, we had t equals p times 1 plus r over n raised to the nt. He was interested in this portion of it. And he wanted to know, what does that value approach as n approaches infinity? Well, this was the first approximation of the value e. Here is part of our value for e, 2.7182, and it just keeps going and going and going. Notice it doesn't repeat, it doesn't have a pattern to it, it doesn't stop. E is an irrational number just like pi is. Okay, so you have to remember E is a number. It is not a variable. It is a number just like pi is a number. It's irrational, so it doesn't repeat, it doesn't stop. On your calculator, you should have a button. More than likely it's going to look like that, E with a raised to sign, or it might be an e to the x type of button, but on your calculator somewhere you will probably have an e button. Okay, so now when we have continuously compounded interest, we have a slightly different formula to use. The I is our initial investment, the P is going to be our final payout, the R is our annual interest rate, and the T is the time of years. And remember, E is just a number. So let's say that Joanne invests $2,000 and it's compounded continuously for 30 years at 4.4%. How much will she have at the end of the 30 years? Well, if we set up our formula, I have to take my initial investment, which is $2,000. I have to times that by E raised to the RT. Well, now make sure you change the 4.4 to a decimal, so it's 0.044 times, and my t now is 30 years. Okay, when I multiply that out, you have to do this piece first, because you have to follow your order of operations, and exponents comes before multiply. So when I take and multiply this all out, I end up getting 7,486.84. So she'd have $7,486 in her account if this were to happen. And that's when it's compounded continuously. Okay, now we can also graph E. The graph of E is going to be an exponential because it fits into that family. Our exponent is in the variable, which makes it an exponential function. So when we go to graph E, we're still going to do just a regular table of values. And I'm going to pick my values to be -2, -1, 0, 1, and 2 to start with. Remember, you can always add more if you need. Now when I plug these in, I'm going to do e raised to the -2. Remember, that does not make my value negative. It makes it 1 over e squared. And when I calculate that out, I get 0.1353. When I plug in -1, I get 0.368. 0 is going to give me 1. 1 gives me 2.718. 2 gives me 7.389. If I add 4 down to my table here, it gives me 20.08. So now when I go to plot these points, if I go to -2 and 0.13, and then -1, 0.3, 0 takes me up to 1, 1 takes me up to 2.7, 2 takes me up to 7, and then 3 would take me up to 20 something, which is going to be up here. Notice it has the exact same shape as an exponential. We have our horizontal asymptote here at y equals 0. Our end behaviors are the same. As x approaches positive infinity, my graph approaches positive infinity. As x approaches negative infinity, my graph approaches 0. So it's still an exponential, it's just a special exponential because it's an e.